Alright, so a fission reaction, we need to find out how much energy is released. What we're going to do in this problem, just the overview, is we're going to use these counting equations, which is that the total energy is equal to the number of reactions times the energy in one reaction. And the total mass of uranium, for example, here, is equal to the number of reactions times the mass of uranium. Okay? Now, we're given the total energy of 2.0 billion kilowatt hours, right? 2 times 10 to the 9th kilowatt hours. And we can find the energy of reaction with delta MC squared, right? So our first step is going to be finding the energy of a reaction. And then our second step is going to be setting that equal to this so we can find the number of reactions. And then we're going to take that n and we're going to plunk it in over here and combine it with the mass of uranium in step 3, and that's going to give us the total mass. Okay? So that's the sort of the roadmap of the problem. If you haven't already tried to work it, then you should do that now before you watch me. So the input mass is proton mass. Neutron mass. My bad. 008665, and a uranium. Uranium is 235.043923. Okay, and the output mass is, you got the strontium, and all these masses are given. This is 87.905614, and then the xenon mass, 135.907220 plus 12 neutrons, so 1.00. Oh no, I'm going off the page. Am I going to make it? Yes, just barely. Wasn't that exciting? Alright, so the energy then in one reaction is delta MC squared, which is the mass of the input minus the mass of the output times C squared. So if I take this and I subtract this, I get 0.135774 AMU times C squared. So I can, if I want to convert that into an energy, I can take 0.135774 UC squared, and I can multiply by 931.5 MeV per mu C squared. Right? That converts this into an energy. So that's 126.5 MeV. And I'm going to want this in joules, so I'm going to multiply by 10 to the minus 13 joules per MeV. So that's 2.02 times 10 to the minus 11 joules. Alright, now the total energy, that's given to be 2 times 10 to the 9th kilowatt hours. Well, I need to convert that into MKS units as well. Our conversion factor from the formula sheet is that it's 3.6 million joules per kilowatt hour. So that's 7.2 times 10 to the 15th joules. Okay? Joules. Okay. Now we're going to come back and we're going to use this equation up here on the top. We're going to find n, the number of reactions, is equal to the total energy divided by the energy of one reaction. Right? Where the total energy is here, the energy per reaction is here. So 7.2 times 10 to the 15th divided by 2.02 times 10 to the minus 11. That's 3.6 times 10 to the 26th reactions. Okay? Now the last step is going to plug the n reaction in over here, and I'm going to find the total mass. So the total mass is the number of reactions, which is this, 3.6 times 10 to the 26th. Now I'm going to multiply. I want to know how much uranium I need, so I'm going to multiply by 235 AMU, and then I'm going to convert that into kilograms by multiplying by my conversion factor. And that is 140 kilograms. That's how much uranium would be needed to satisfy TCU's energy needs in 1 year, just about.